Hello, and welcome to our AP Chemistry review of topic 8.3, weak acid and base equilibria. In this video, we're going to cover a lot of stuff, so we're probably going to go over my always planned 10 minutes, but we'll see how long this one takes us, because there's a lot to cover in here, and I'm going to do a couple of practice problems also. So when we talk about weak acids and weak bases, the first thing that's really important to realize is that weak means partial dissociation. So when we say weak acid, we're talking about an acid that only partially dissociates, as opposed to a strong acid, which 100% dissociates. And so, for example, HCl, which we've talked about in the past, is a strong acid. And so when we place it in water, 100% of the molecules of HCl are going to dissociate and produce hydronium ions and chloride ions. 100%. That's what makes a strong acid a strong acid. Weak acids, on the other hand, such as hydrofluoric acid, does not ionize 100%. Hydrofluoric acid will only partially ionize when it's placed in water. And so when I put it in water, it's going to set up an equilibrium where some of the molecules ionize and some of the molecules will not. And so it's going to be a lot less than 100%, and typically a whole lot less than 100%. And that's what makes a weak acid or a weak base weak, is partial dissociation or partial ionization. So whenever you have a weak acid, you're going to have much more of the acid present in the solution than you are the hydronium ion. And so how much hydronium you're going to have produced in a solution depends on the concentration of the acid and the Ka value, the equilibrium constant for the hydrolysis of that acid, for putting the acid in water. So we can write an equilibrium expression for these weak acid and weak base reactions, and we'll talk about bases more in a minute. But the equilibrium constant for an acid placed in water is given by the equation Ka, and I was a little lazy here, and I shouldn't have been lazy. I should have put the states of matter. Acid is aqueous, water is a liquid, of course, and then our ions that are produced are also aqueous. And so when we write an equilibrium expression, we're going to put the concentration of our products, which is the H3O positive, times the anion concentration, divided by the concentration of the original acid. And so if you look at this, this is the way that we can write the equilibrium expression for any acid placed in water. And that equilibrium is represented by Ka. It's always going to be hydronium and the anion of your acid, which is also called the conjugate base. And then the acid itself is going to be in the denominator. Ka values can be looked up on tables. There are tables of Ka values. And if you know the Ka value, you can know the relative strength of the acid. So I have a Ka table here, a table of equilibrium constants for acids. You'll notice that up at the top I have the strong acids, and because they're strong acids and they dissociate 100%, their Ka is much greater than 1, much greater than 1. We assume that they dissociate 100%. But as you get down to the weak acids, iotic, I've just given you part of a table here. They give you I have the formulas here, but you'll notice I have the Ka values for each of these. And notice that they have the higher Ka values at the top, lower Ka values at the bottom. The smaller your Ka value gets, the weaker the acid is. In other words, the less product favored the reactant is. Remember, if a K value is less than 1, it's going to be reactant favored, meaning that your acid is going to stay intact and it's going to make less and less product. Notice for hydrofluoric acid, I have hydrofluoric acid on here. The Ka value is 7.2 times 10 to the negative 4. That is much less than 1, and so very little of the HF actually dissociates. Very little of the HF actually ionizes. Only some of it's going to ionize and produce hydronium and fluoride. Because we don't make a whole lot of hydronium, we would expect higher pHs than for strong acids of equal concentration. So one of the tasks that you're going to be asked on the AP test is, how do you calculate the pH of a weak acid if you're given the initial concentration of the weak acid? So we're going to go ahead and do a couple of calculations here and figure out how to calculate the pH of a weak acid given its initial concentration. So the acid we're going to work with is HF, since I already have, we've already been talking about that a little bit. I'm going to give the problem, and let's say, what is the pH of a 0.54 molar HF solution. And right now we're just dealing with weak acids. We'll deal with weak bases in just a little bit. So how are we going to solve this problem? Well, this is an equilibrium problem. So we're going to set up a rice table. We're going to write down the reaction, the R in rice. So our hydrofluoric acid, which is aqueous because we're putting it in water, and it's going to produce hydronium, which is H3O positive, and this is aqueous, and fluoride, which is also aqueous. Just a reminder, this is our acid. The HF is our acid. H2O is going to behave like a base because it's giving away a hydrogen ion. Our conjugate acid, the substance that gained the hydrogen, is our conjugate acid, and the substance that lost the hydrogen is our conjugate base. We're going to talk more about bases in just a little bit, but in any of these reactions, in any of these hydrolysis reactions, you always have an acid and you always have a conjugate base. All right, so rice table. What are our initial concentrations? Well, our initial concentration of HF is 0.54 molar. Water doesn't have a concentration because it is a liquid, so we don't need to deal with its concentration. Hydronium, there's always some hydronium in water, but if you recall, the concentration of hydronium in pure water is 1 times 10 to the negative 7. And 10 to the negative 7 is very, very, very small compared to 0.54. That's an order of magnitude of a million different. And so we are going to assume that the initial concentration of hydronium is 0 molar. Even though there's a small amount from the water, it's so small we can assume that it's 0. And then, of course, there's no fluoride initially right when I put the HF into the solution. So initially 0. Change. What is our change? Well, HF is going to lose some amount due to the hydrolysis, due to the ionization. The hydronium is going to gain stoichiometrically X amount because it's a 1-to-1 ratio. So for every amount of HF I lose, I'm going to gain the same amount of hydronium, and I'm going to gain the same amount of fluoride. And then our equilibrium concentrations are going to be 0.54 molar minus X, 0 plus X, which is X, and 0 plus X, which is X. So how are we going to solve this problem? Well, we're going to use the equilibrium expression, the Ka expression. So the Ka for hydrofluoric acid is the products, which is H3O positive, times the anion or conjugate base, which is fluoride, divided by the concentration of the original acid, which is HF. And now we can substitute our equilibrium amounts into this expression. So our Ka value, if we go back up and look up hydrofluoric acid's Ka value, it's 7.2 times 10 to the negative 4. So that's what we're going to plug in for the Ka. Now we're going to plug in our equilibrium amount. So at equilibrium, we're going to have X amount of H3O positive multiplied by X amount of fluoride divided by the concentration of the HF at equilibrium, which is 0.54 minus X. Now this is where we get to decide if we get to use a shortcut so that we can avoid a quadratic equation. Because if you'll notice, X times X is X squared, and in the denominator we have a single X. So this is a quadratic, and if we solve this straight from this equation, we would have to use the quadratic equation, which of course slows us down a little bit. So there's a shortcut. We can look at the concentration of our acid. And the concentration of our acid was originally 0.54. And we look at our Ka value, which is magnitude times 10 to the negative 4. If your concentration of the acid, and I'm just going to use the generic HA for weak acid, if the concentration of the acid is originally much greater than 100 times the Ka value, then we can eliminate this minus X. And the reason we can do that is because the X value, the amount of change in this at equilibrium, is going to be much, much smaller than 0.54. And so significant digit-wise, subtracting X is not going to affect that concentration 0.54. And you can check that at the end to see if the assumption was valid. We'll subtract and see if 0.54 changes any. But if your concentration of acid is greater than 100 times the Ka value, we can ignore it. So 0.54 is indeed well over 100 times our Ka value. So what we can do is we can eliminate this minus x. So now it's just a matter of solving for x. So I'm going to simplify those x's. 7.2 times 10 to the negative 4 equals x squared over 0.54. And remember, if we solve for x, we will get the concentration of hydronium. And if we get the concentration of hydronium, we can solve for the pH using the pH equation. So now we are going to solve for x, which is just going to be an algebraic manipulation. And if you do that, you get an x value of 0.020 molar. And remember, x is the value of our hydronium concentration at equilibrium. So this is our hydronium concentration. And again, if we know the hydronium concentration, we can solve for the pH. Now, this is where we can check and see if our assumption, the minus x, actually would have made a difference. So 0.02 and 0.54. 0.54 minus 0.02 does change this value slightly. And so our x value is definitely going to be just a little bit off. But because it is very small compared to the 0.54, we can assume that our assumption was correct. That the minus x did not affect the overall value of x. Getting rid of the minus x in our equation was a valid assumption. So now it's just a matter of solving for the pH. So pH is going to equal the negative log of the hydronium concentration. So if we plug in our hydronium concentration, our x value, we get 0.020. Solving for the pH, we get a value of 1.70. And so that is the pH of our weak acid solution. So what about bases? How would we do this type of problem for a base? Well, first, let's talk about bases. So a weak base is definitionally similar to weak acid as far as setting up an equilibrium. So if we have a weak base, let's say that we had ammonia. Ammonia is a weak base. When we put ammonia in water, making this aqueous, and water is a liquid. When we put it in water, ammonia is going to pull a hydrogen ion off of water to make NH4 positive, which is the ammonium cation, and OH, because water loses a hydrogen. And so this is going to be our equilibrium. This only happens to a small extent. Very little of NH3 will actually pull a hydrogen off of water to produce ammonium and hydroxide, but some do, and that's why it is a base. So this is our base. Water is going to behave like an acid because it's giving away a hydrogen ion. Ammonia, after it gains a hydrogen ion, becomes the conjugate acid. Remember, the base, after it gains a hydrogen ion, becomes a conjugate acid, and then OH is our conjugate base. The acid, after it loses a hydrogen ion, becomes the conjugate base. And so this happens to a small extent. So how can we figure out what extent it does happen to? Well, we can use a Kb value, an equilibrium constant for a base. So since this is a base, we call it Kb, the equilibrium expression. And again, it's just like the acid one. It's our products over our reactants. So the concentration of ammonium times the concentration of hydroxide divided by the concentration of our original base. And so this is our equilibrium expression. We call it Kb for our equilibrium constant because this is the equilibrium constant for a base hydrolysis. And again, these Ka values and Kb values are for when an acid is placed in water or when a base is placed in water. So this is our expression. So now you can see that we could solve another problem just like we solved in the last one to solve for the pH of a particular base. Except this time, instead of solving for hydronium, we'll have to solve for hydroxide and then use the POH equation to solve for the POH and then solve for the pH. So let's try this one. By the way, the Kb value for ammonia is 1.8 times 10 to the negative 5. So that's our Kb value for ammonia. All right, so that's the problem we're going to solve. So again, how are we going to solve for pH? Well, we first have to solve for the hydroxide concentration. And then once we know the hydroxide concentration, we can solve for the POH. And then from the POH, we can solve for the pH. So very similar to the last problem. So let's go ahead and set up our rice table. So for our rice table, the reaction, what's our next step? Well, what's the initial concentration? So our initial concentration of ammonia is 0.12, which was given to us in this problem. So 0.12 molar. Water is a liquid, so we don't have to worry about it at all. Our ammonium, there is no ammonium in this solution initially. Right when we put the NH3 in, there's no ammonium present initially. And then hydroxide, again, water does have some hydroxide in it, but hydroxide concentrations in pure water are 1 times 10 to the negative 7. That is very, very small. That's 1,000,000 times smaller than our concentration of our ammonia. And so we can assume that the hydroxide concentration is 0 initially. So change. Well, we're going to lose some ammonia in this equilibrium. We're going to gain some ammonium in the same ratio, stoichiometric ratio, so plus X. And then hydroxide, we're also going to gain plus X. Our equilibrium amount is 0.12 molar minus X. X for the ammonium and X for the hydroxide. So now we have to decide, can we ignore this minus X or not? And again, we're going to use the 100 times rule. Is the concentration, 0.12, over 100 times greater than the Kb value? And so when we look at the Kb value, which is up here, 1.8 times 10 to the negative 5, that is definitely 100 times smaller, well over 100 times smaller than the original concentration of 0.12. So we can ignore the X here, but you do always have to check to make sure you can ignore the X. Is it 100 times smaller than the Kb value? So now we're going to solve for the hydroxide concentration by using the equilibrium expression. So let's go ahead and do that. And now we're going to substitute in the equilibrium concentrations. So and our Kb values. So now it's a matter of solving for X, because remember, X is the hydroxide concentration. And if we can solve for that hydroxide concentration, then we can solve for the pH. So if we go ahead and algebraically solve for X, we get 0.0015 molar. And so that's going to be our concentration of hydroxide. So at this point, we know the concentration of hydroxide. We're going to solve for the POH. The POH is the negative log of the hydroxide concentration. So if we plug in the hydroxide concentration and take the negative log of that concentration, so 0.0015, then we can get the POH. And you'll want to leave the whole number, not 0.0015, but the whole entire number on your calculator and take the negative log of that. And that gives us a POH of 2.83. Notice there's 2 significant digits in the concentration, so my POH has 2 decimals, because only decimals in POHs are significant. So now that we know the POH, we can calculate the pH. So remember that pH plus POH is equal to 14.00. And again, that's only true at 25 degrees Celsius. Since I didn't mention temperatures anywhere, we're going to assume this is at 25 degrees Celsius and solve the problem with 14. If the temperature was different, then pH plus POH will equal something different than 14. So now we can solve for the pH by taking 14.00 and subtracting the POH, 2.83. You get 11.17. And so that is our pH of this weak base solution. And that answer does make sense. We should expect a value that's quite a bit less than 14, but above 7, of course. So that's our pH. So that answer does make sense. So that's how we solve for the pH of a weak acid and the pH of a weak base. A couple other little pickup things. A lot of times you might not be given the Ka value, you might be given the pKa value. And so pKa is equal to the negative log of the Ka. It's kind of like pH. It simplifies these values because Kas have very small magnitudes, times 10 to the negative 5, times 10 to the negative 6. So pKa is often an easier way to represent that. So just know that sometimes if you're given the pKa, you'll have to use this equation to solve for the Ka. And the same is true for Kb. Instead of the Kb, you're sometimes given the pKb. And so if you need the Kb, you can solve using the pKb using this equation. The other thing to know, and we'll use this more later, is that the Ka value times the Kb value equal to Kw. And Kw, if you recall, is 1.00 times 10 to the negative 14 at 25 degrees Celsius. So if you're given the Ka value for an weak acid, the Kb value for its conjugate base would be able to be calculated using this equation. Ka times Kb equals 1 times 10 to the negative 14. And again, that's for an acid and its conjugate base, or a base and its conjugate acid. So that is our introduction to weak acid and base equilibria. There's a lot of stuff packed in there. Hopefully that was helpful in practicing these problems. I wish you the best of luck as you study. And if you have any questions, as always, please let me know. Bye-bye.